Let's wait a bit. Okay, so not much today, just one section. So yeah, okay. So whiteboard. So our goal is to generalize, study polynomials, right? So polynomials. So obviously we want to consider, something that encapsulates that. So we're gonna make a ring pretty much. It's called like the ring of polynomials. So let X be indeterminate. Right? It's just like a set. It's just like a set object. Don't think of X as like an input or anything. So let R be ring. Define polynomial f of X. So this is just notation with coefficients in R to be infinite sum, formal sum. Right, so obviously a polynomial can't have infinitely many terms, right? But we just say all but finitely many are 0. AI x to the I plus A1x to the n, right? Where all but finitely many AI are 0. And AI are all in our ring. So my first question to you all would be, what does formal mean? Can anyone take a guess? Or what do we mean by a formal sum? Direct. So what would indirect be? If you call this direct, like what would indirect be? So does anyone else have any ideas? Or okay, so in math what? Math 2B, or if you took it, or maybe you skipped it. What is a sum? So let me just say in calculus, like what is this thing? It's defined to be something like this, right? If you recall correctly, 0 to n. Everyone remember this? So, and then this goes on to be like, you have all, definition of limits and stuff like that, right? Definition of limits. Of limits, etc. So we don't want to deal with any of this. So this is formal just means, as just define this as it is. So there's like no limits, no radius of convergence, stuff like that. Yeah. We're not, so like no calculus, right? We're just constructing this object, without introducing stuff like limits, radius of convergence, stuff like that. Everyone, so that's what formal means. Yeah. Everyone follow so far? Because if you need to actually define a sum, you work from here, and we don't want to do that. So, okay. Okay. So obviously the elements of R, these are elements of R are like the constants, right? So, think of these as like the constants. Okay. So how do we add and how do we subtract, right? F of x is dot. G of x is this. Because again, we want to make a ring, right? So we have to define what addition is and multiplication is, right? So addition is what you think, right? It's dot c and x to the n, where so is this a binary operation? Is addition a binary operation here? So am I mapping upon, is this a polynomial I get?
Yeah.
Yeah, right. Because we define polynomial as it's an infinite thing where all but finitely many are zero, right? So if all but finitely many are zero here, all but finitely many are zero here, I think it's pretty clear that all but finitely many are going to be zero here, right? And same for multiplication. It's going to be, just the FOIL law, right? You're just foiling. So where dn is I equals 0 to n ai bn minus I, right? Because again, how do you get x to the n? Well, you could do x to the I times x to the n minus I, right? And then you just locate the coefficients. So like this is the coefficient of x to the I, right? If you look at what f is, right? And this is the coefficient of x to the n minus I, right? And then you run through all of that, right? So if n was like 5, for example, then you go x to the fourth, and then x squared, x cubed, x squared, and then x to the fourth x, right? So, I mean, it's just FOIL law. And it's clear that this is a binary operation because if all but finitely many are 0 above, then it's pretty clear all but finitely many 0 are in the product, right? Okay, so R of x, you could check that if we define R of x to be the set of all polynomials in indeterminate x with coefficients in R, ring R. So you could check that this forms a ring. Yeah. Okay. So really quickly, right? There's an isom. Let me just say there is an isomorphism between R of X of Y and R of X, R of Y of X. Can anyone tell me a priori why these two rings are different? So how did I define R of X? These are polynomials in variable X where R is my constants, right? So this is like sum of AI y to the I, where AI is in R of X, right? Elements here is sum AI x to the I, where, I guess I should put where AI are in R of Y. Everyone see this? And I mean, it's pretty clear, once you just combine the X and then the Y's, and then it becomes literally like the same ring. But a priori, these two are like two different objects, right? From how we defined, I guess, the ring of polynomials. But it turns out that there's an isomorphism between them. So from here, right, we since they're isomorphic, it doesn't really matter which one we use. So we just call this ring R of xy for simplicity. And then similarly, you can do that for, I mean, the proof would just be by induction, right? You similarly, we do the same for R of x1 to xn. So again, like if you want to, in English, this is the ring of polynomials in two indeterminants. Xy with coefficients in R. Right? And this would be like, this is xn. This would be like n determinants, right? Okay, everyone follow? So obviously we have a famous homomorphism involving these. It's called evaluation. Homomorphism. It's pretty clear, right? Because if you have a polynomial, think of like calculus. If you had like a polynomial, you could forget calculus. If you had a polynomial like in algebra, like you can always evaluate it at some point, right? So that's sort of what we do here. But we be a little more general. Subfield of E, alpha is in E. Then we could evaluate. Then phi alpha is just evaluating at alpha. So this is f of x is a field. We go to E, where we send f of x to f of alpha. Yeah. Okay, so let's do some problems. Yeah, in the book. So example. How many polynomials are there of degree less than or equal to 2 in Z5 of X? Yeah, so my R in this case is Z5, right? So how many are there? Any ideas? So let's count, yeah? Does everyone agree that any polynomial of degree 2 or smaller than 2 is gonna look like this, right?
Yeah.
If it was like degree 1, then a is just 0, right? So how many choices for a do I have? This is a counting argument. So how many choices of A do I have? We're in Z5, Z mod 5Z. So, okay, what about B?
5.
Yeah. C?
5 again.
Yeah. So, what is that? 125? Yeah. Everyone clear on this? It shouldn't be that hard. Okay, so what other things can we do with polynomials? Well, we could find zeros, right? So find zeros. In indicated field of given polynomial. That that would be a choice too. We included everything, right? We said there were 5 choices for A, right? That includes 0 because the 5 choices is we're in Z5, right? So it's 0, 1, 2, 3, 4, right? So yeah, one of the case would be 0, 0, 0, right? Can read. Yeah, that would be the 0 polynomial. Exactly. Okay, given polynomial with coefficients in that field. I mean, if it really bothers you, you just write it out, right? So, I mean, I'm not gonna write out all 125, but you know, you could say let's set a to be 0, then I have like choices here. Right? I have 0, 0, 0. So this is for like A, B, C, right? And then 0, I don't know, 0, 1, 0, 0, 2, right? 0, 0. I'll write out some of them, right? And then you have like 0, 1, 1, 0, 1, sorry, 0, 1, 1, 0, 1, 2, 0, 1, 3, 0, 1, 4. I don't know why I forgot 0, 1, 0, but and then the list goes on and on, right? So there's like 125 of them. So yeah. Okay. Okay, so moving on. So let's find zeros in this field. So let's do x squared plus 1. So this is in Z2. Yeah. So all the coefficients are in, we view them as in Z2, and then we're trying to find the zeros in Z2. So what do we do? Uh, everyone, it's not that hard. You just C2 has 2 elements, so you just plug in the 2 elements. What are the 2 elements? 0, right? Is 0 squared plus 1 0? In Z2, of course. Is 0 squared plus 1? does that give? No. What about 1 squared plus 1? Yeah. 1 squared plus 1 is 2, right? 2 is 0 in z mod 2z. So, or sorry, if you like, this is z mod 2z. So, like here, there's the zeros is just x equals 1, right? But you can also see that this is multiple root, right? Because what is minus 1 in z mod 2z? Can anyone tell me? Well, what is minus 1? Is that 1 or 0? So I could change this to, yeah? And this is, you all know the rule. but minus 1 is just plus 1, right? Or if you like, this is just plus 1 is minus 1. So here, this is just this in z mod 2z, yeah? So in fact, it's a 0, but it's like the 0 of multiplicity 2, right? Of course, the question never asked for multiplicity, but just so you all know. Okay, let's do something more different. X cubed plus 2x plus 2. Just so we're all clear on this, let's do one more simple one. So how would you do this? So again, you have, I guess, how many elements? 7. So 0 doesn't work, right? 0 gives 2. 2 is not 0 in z mod 7z, right? So now you try 1. 1 gives 5, right? So that's a no-no. 2 gives, what is that? 2 cubed is 8, which is 1. So 1 plus 4 plus 2, is that 0? Yeah, so x equals 2 works, right? And then x equals 3. So let me just write x equals 0. No. Works. X equals 3. 27. 3 cubed is 27. 27 is -1, right? Mod, or 27 is 6, right? 6 plus 6 plus 2, 14. Yeah, so x equals 3 works. And for people who want a trick, right, you don't have to do 4 cubed because 4 is -3, right? So you could plug in -3 instead. So you get -27. -27 is 1, right? Minus 6 plus 2. So that's -5 plus 2, which is -3. So that's no. I mean, it's not a multiple of 7. And then you try -2, so -8 minus 4 plus 2. This is a bit easier. So -12 plus 2 is -10. So this is also no. And last one, -1, obviously doesn't work. Yeah, so these are your 2 zeros. Yeah, x equals 2, x equals 3. Everyone clear on this? Okay, so how about this one? 2x to the 219, 74. So this should cover, all the hard stuff in this homework. In z mod 5z. So if you see this, obviously, don't plug in. I mean, you. Sorry. Yeah, 57. Okay, there's an obvious 0. What is it? It's x equals what? there's an obvious one.
0.
Because there's no constant term, right? Like, yeah, and obviously x equals 1 is also 1, right? Because 1 to any power is 1. So 2 plus 3, 2 plus 3. Okay. So what else? So you don't want to plug in 2, right? I mean, you sort of do, but what is 2 to the 219 mod 5? We did this last time. What does Fermat-Little theorem tell you? Fermat-Little theorem. So yeah, I think it's called Fermat-Little theorem. Do you all remember the thing with like a to the p minus 1 is congruent to 1, right? So I know 2 to the 4th is congruent, not forget 2, just we did 0 already, right? So a to the 4th is congruent to 1 mod 5. For in this case, for a not 0, right? Because everything else is co-prime to 5. So here I know that this for 2, right? For x equals 2, I could work with something easier. This is 2. How much does 4 go into 219? So what remainder do you get when you like x to the, I think 216 is divisible by 4, right? So does everyone agree that I could write 219 as this, and then this is just 1, right? Because this is just some multiple of 4, and I know whatever to the 4th is 1. So this is 2x cubed plus 3. 72 goes into 4, so this is 3x squared plus 2. 56 goes into 4, right? So this is just 2x. And this is just, what is that? This is completely a multiple 4. So this is just 3, right? So now this is easier, right? 2 times 2 cubed plus 3 times 2 squared plus 2 times 2. Like this is way much easier to calculate than like the original expression, right? So this is what, 816 plus 12 plus 4 plus 3. 16 mod 5 is 1. So that's 1 plus 2 plus 4 plus 3. What is that? 3 plus 3 is 6, 10. So this works, right? X equals 2 is also a root. Is everyone clear on how to do this? Yes? No? Okay. I will let you check 3 and 4 for practice, but for 3 and 4, right? Do not use 3 and 4. Use -2. And I guess negative 1, right? Those are easier to check. I mean, in fact, we could check -1 here. Let's just do it. So -1 gives you -2, -2. Yeah, so x equals -1, that doesn't work, right? If I do my algebra correctly. Yeah, and then -2 is what? So I get -16. Let's maybe erase this. So again, all I did was just plug in -1 to this equation. So -2 is what? -16 plus 12 minus 4 plus 3. So that's -4 minus 4 plus 3. So -8 plus 3 is negative. Oh, it works. Yeah. So everything is a root except -1, which is 4. in Z mod 5Z. Okay, everyone follow with this? So now I'm going to move on. So if I have an integral domain, units, one can, if D of X, where D is integral domain, what are the units? So if I tell you a polynomial, what's the unit of a polynomial? So a standard example would be, right, what's the inverse to 1 minus x? So what would you say if I didn't tell you this was a polynomial ring? What thing do you multiply to 1 over x? I mean, sorry, I'm trying to get it. What thing do you multiply to 1 minus x to get 1? So times, this is times, by the way. So what's this question mark? I mean, just solve for it. So what is it? This is an example. Not a trick question. You can all do this. Yeah, good. Everyone follow? So, okay, now this, right? This doesn't lie in our polynomial ring, right? Because first off, it's not a polynomial. It's not a polynomial. So later on, I'm not sure if the class goes over, but we might go in the power series ring. And in this case, it would be an element, right? Because if you remember from calculus, this is just sum n equals 0 to infinity x to the n, right? Do you all remember this? Because if I multiply 1 minus x to this thing is just 1 plus x squared plus x cubed infinitely many times, right? So if you just think about it, if I just FOIL to the 1 on everything, what do I get? If I just FOIL the 1, I just get this, right? Now, what happens if I FOIL the x? X times 1 is x, right? So FOIL means I'm sort of adding, right? X times 1, or I guess subtracting, since it's a minus sign here. So subtracting x times 1 is x times x is x squared, x times x squared is x cubed, ... right? And what you're going to see is everything is going to cancel out except 1. Yeah. So you sort of see that this is the inverse, but it's not a polynomial, right? So you see, like, an example would be like 1 minus x is not invertible in d of x, right? Because the inverse does not lie in is not a polynomial, right? It's some infinite thing, right? Remember, a polynomial it's an infinite series, but only all but finitely many terms are 0, right? Here, this is not the case. There's infinitely many coefficients that are 0. In fact, they're all coefficient 1, right? All AIs are like 1. Does everyone see this? Yes or no? Please give me an answer. Is everyone following? Okay. So it turns out that what are the units? Well, it turns out it follows this really easy concept of degrees, right? So if I have like f of x is degree n, g of x is degree m. Since we're in an integral domain, degree actually makes sense as a product. So what's degree of f times g? I mean, if you want, just take n and m to be like numbers. So take n to be 5, right? M to be. Oh, by the way, it's actually it's just this, right? For integrals, of course, we're fg in d. Yeah, we have no zero divisors, right? Because we're in an integral domain. So f of x, we're in an integral domain. So what does unit mean? So if I gave you f of x, right? I need to find a g, right? A g such that this is 1, right? But what's degree of this? If these are equal, then degree should be equal, right? So, so degree of f of x plus degree of g of x is 0. So what you're going to notice is, one, if from here, right, just from here alone, one, if d of x has units, it must be degree 0, but degree 0 is just constant, right? It must be a constant. Does everyone agree with this? From here, I mean, you can't have negative degree, right? So like both of these must be 0 for them to sum up to 0, right? So it must be a constant, but then you're just asking, you know, what are units of, so what are units of d, right? So since constants are just elements of d, then there's your answer, right? The units of d of x are the units of d. Right. So it's sort of, you know, hopefully it's portrayed here, right? Once you have a polynomial, the inverse is sort of like a power series, right? You can't really have finitely many things. You need some infinite thing to get rid of, you know, your terms. Does everyone follow with this? Yes. No. Okay. So one last thing, and then we'll call it a day. So we said that, you know, over integral domain, this is equality, right? But it certainly need not be the case for non-integral domains, which is another reason why we hate them. But so let me just ask one last question. So find a polynomial of degree greater than 0 in Z4 of X. Actually, I'll go over one more, just to portray something. That is a unit. I kind of skipped the question because I missed it, but here, right? Find the polynomial of degree bigger than equal to bigger than 0. And the point is, it's possible for things to cancel, right? So to be a unit, right? So basically you want like, so let's take linear term, right? That seems to be the easiest, right? If we want degree bigger than 0, might as well work with degree 1, right? So I need, you know, x plus, let me just say a1, a2, a3. I want these two to cancel, right? Because I want the x squared term and then the x term to cancel, right? So obviously, if I want the x squared term, the only option I have here, I can't have 0, right? Because if I have 0, it's not linear anymore. So what's the other non-unit in Z mod 4Z that's not 0? Yeah, I need this to be 2, right? These to be 2. So now when I do FOIL law, right, the x squared term goes away. Now from here, let me just A2, A4. So this one, I need these to be inverses, right? So what's the inverse of, let's just choose one of the elements, right? What's the inverse of 3 in Z mod 4Z? If I choose this to be a unit, the inverse of 3 is 3, right? Because 3 times 3 is 9. And sure enough, you can check that this is 4x squared plus 12x, right? Plus 9. This is 0, this is 0, and this is 1. Yeah. So you start to see here, like this is f, this is g, but degree of f times g is 0, while degree of f plus degree of g is 2. Yeah, so it's not always the case in like non-integral domains. And in fact, it's much worse, right? You can get a unit. A polynomial can be a unit, a non-constant one, I mean. So let me just say, right, aside from characteristic 2, people might ask, right, if I say find zeros of x squared plus x plus 3, right? Some students, I think, might ask, like, can I use quadratic formula? And the answer is yes. So if I use quadratic formula, but you have to be very careful. Let's sort of write out what quadratic formula is, right? X equals negative b, so that's -1 plus minus square root. So square root, you think it through, right? So b squared is 1 minus 4ac all over 2a, right? But you have to think about it in the operations of Z5. So here, right, this is -11, right? Or at least I think it is. 1 minus 12. Okay, yeah. Normally, square root of -11 has no solution, right? But what is -11 in Z mod 5Z? In terms of the numbers 0, 1, 2, 3, 4. It's 4, right? Just keep adding 5. So -11 plus 5 is -6. -6 plus 5 is -1. -1 plus 5 is 4, right? Okay, so now this has a square root because, I mean, this is in fact pretty easy because it's 2, right? So now I have negative, what is that? I have 1/2 and -3/2, right? -3/2 is just 2 over 2, right? Because -3 is just 2, right? So this is sorry, this should not be equal, but rather, I'm doing the plus minus, right? So you have like 2 solutions. So this one is just 2 over 2, so that's just 1. What is 1/2? So what does half mean? What does dividing by 2 mean in Z mod 5Z? Dividing by 2 in Z mod 5Z is multiplying by what? By 2 inverse, right? Does everyone agree? So, I mean, in this case, 2 times 2 inverse is 1. But here, right, this is 1 times 2 inverse. What's the inverse of 2 in Z mod 5Z? 3. Yeah, so your answer is 1 and 3. And sure enough, right, like plug it in. You could try it. I mean, in this case, it's faster to just plug in. But 1 squared plus 1 plus 3 is 5. That's 0. And then 3 squared plus 3 plus 3, that's what? 15. That's also 0. Yeah. So, and in some cases, if the square root doesn't, the square root, like, not everything can be square root. Like you can't square root everything in like z mod 5z, right? For example, because you can just check it, right? 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 1, 3 squared is 4, right? 4 squared is 1, right? So you see, square root of 2 and square root of 3 has no solutions in z mod 5z, right? So if you did quadratic formula and you ended up with like square root of 2, then you know that there's no zeros, right? By the way, for people who are interested in this, this is called quadratic residue. I think you learn it in like Math 180A. It's like along with like quadratic reciprocity and stuff. But anyhow, yeah. So quadratic formula does work, is what I'm saying. Like you could certainly use it if you don't want to plug in. That is another option. But you would have to make sense of what's square root and dividing means. Okay. That's all I have for today. I will see you all next Tuesday.